Hello, welcome to Mystery Science. Today we're looking at stopping distances. Now this forms part of the forces topic, which is CP2 of the Edexcel exam board. Again, this could be used for SP2, and also I think there's a load of elements that can be used in AQA and OCR exam boards as well. So in this lesson, we're going to be looking at human reaction times and how we can measure them. And I've got a little experiment for you to do if you've got somebody else around to help you. We're going to look at what the typical human reaction times are and why that makes a difference to safe driving on the roads. We're going to be looking at the link between stopping distance, thinking distance, and braking distance, and what all of these factors mean, and the different factors that affect them. And then we're going to have a look at how drivers' reactions can be affected by a bunch of different factors, and also what the weather is doing and how that affects stopping distance. Some of it is fairly obvious, some of it might be a bit of a surprise to you. Right, so our normal start then, we have these do now questions. So if a car has a mass of 900 kilograms and has a momentum of 11,700 kilogram meters per second, what is the velocity of the car? Work that one out. I'll go through the answer in a moment. Now then, my passion of ice hockey. If an ice hockey forward has a mass of 97 kilograms, like Jack Eichel, and he travels at 11 meters per second, like Jack Eichel, and collides with a stationary goalie, what will their velocity be after the collision? The goalie has a mass of 102 kilograms, a bit like Linus Ullmark. So this momentum question is about working out the momentum before the collision and the momentum after the collision. Pause the video and we'll see you in a couple of minutes when you've got the answer. All right, so welcome back. To have a look at these questions, we're going to go through an SROW method. Obviously, you know we love the SROW, gets us marks in exams. So the equation, we've been asked about momentum. We've been asked to find the velocity of a car with a specific momentum and a specific mass. So we substitute the numbers we were given into that equation. The momentum is 11,700. The mass is 900 kilograms. That's all multiplied by the velocity. Do we need to rearrange? Yes, we do. We don't have the unknown as a subject of the equation. I want V to be the subject of the equation. So to do that, I need to divide both sides by 900. So rearranging then, I get V equal to 11,700 divided by 900. And that gives me an answer of 13. And that's 13 meters per second because it's a velocity. Right then, on to my ice hockey forward. Now this has happened to me where I've been stationary, blocking the goal, and a forward has charged onto me. He hasn't shot the puck. He's been trying to kind of eke me out, and he thinks that I'm going to drop down to try and save the puck that he hasn't shot. He can then shoot that over my shoulder, but I haven't moved. So what tends to happen is there's a collision. And because the goalie is not moving, now this is simplified, the goalies are actually normally moving backwards, but because the goalie is not moving, their total momentum is 0. So to work out these questions, we have to work out what the momentum is before the collision and the momentum after the collision. So momentum is mass times velocity. So mass times velocity before the collision has to be equal to the mass times velocity after the collision. With me so far? Good. Now, we've got two bodies. We've got the body of the forward, Jack Eichel, and we've got the body of the goalie, Linus Ullmark. So we have to add the momentum of these two bodies together to get the total momentum before the collision. The total momentum after the collision, they join together and they both move off together. So their momentum is the same. So we substitute in the numbers now. We have 97 times 11, that's momentum for Jack. 102 times 0, that's momentum for Linus. And then after the collision, we've got their combined mass, 97 plus 102, multiplied by their velocity. Remember, they're moving off as one body. Now, it's not going to surprise you to know, hopefully, that if the forward is going at 11 meters per second, and he collides with a goalie, and the goalie is heavier than him, then the resultant velocity that they're going to move off in is going to be less. So we're looking for a number that's less than 11. So our total momentum is 1067 kilograms meters per second plus 0. The momentum of Linus Ullmark is 0 because he's not moving. He just has mass. Their combined mass together is 199. So I can rewrite the equation. 1067 plus 0 is equal to 199 multiplied by their final velocity. Okay? So we resolve all that down. We get rid of the 0. So 1067 is equal to 199 times velocity. So to get the velocity on its own, I have to divide both sides by 199. So the velocity of both of them together is 1067 divided by 199. That's the total momentum before the collision divided by the mass of the two guys together. And that gives you a velocity of 5.36 meters per second, which is perfect because as Jack Eichel streams in at 11 meters per second, he's going to collide with Linus Ullmark, and then they're going to move off backwards, probably in a massive heap in the goal. The referee is going to blow the whistle, take the puck, and then move it over to the face-off spot, and then they're going to have the rest of the game. Right, so when you are learning to drive, you're asked to remember one of these charts, and it's about stopping distances. It essentially tells you how long it takes to stop your car traveling at different speeds. So if you're traveling at 20 miles an hour, it takes you, on average, 12 meters or 40 feet to stop your car from 20 miles an hour to 0 mile an hour. So 12 meters is about 3 car lengths. That's quite a long way. Half of that distance is the thinking distance. Now at 30, you've got 23 meters. At 40, it's 36 meters. At 50, it takes 53 meters. Traveling at 60 miles an hour, it takes 73 meters in order to stop. And at 70 miles an hour, almost 100 meters. That's 96 meters. That's the length of an Olympic sprint track to stop going at 70 miles an hour. So if you are traveling at 70 miles an hour and something jumps out at you and it's closer than 100 meters, there's going to be a collision. Now this is a little bit controversial because these things all have various dependencies. The thinking distance depends on an average person. Some people have better thinking distances and some people have very much worse thinking distances. Now this is the time which your impairment could really hurt you. And also the braking distance depends on both the weather conditions, the surface of the road, but also the state of your vehicle and also the mass of your vehicle. Now these are typical stopping distances for a car. So what I'd like you to think about is, what do you think thinking distance is? What is braking distance? And how do these things both change as the speed increases, and why do they change? Right, so our overall stopping distance is affected by two things: the thinking distance and the braking distance. Now, the braking distance is dependent upon the type of vehicle you're in, how heavy it is, how good the brakes are, how good your tyres are, how sticky your tyres are, and also the road surface and the conditions, if it's icy or if it's wet. And it's the distance taken for the car to stop after you've applied the brakes. So as soon as you pumped your foot on the brake pedal, the distance between that point on the road and your car coming to a complete stop is called the braking distance. Now, as you can imagine, if your road is covered in ice, then that's going to be considerably further than if it isn't. And if your car is not doing so well and it hasn't passed an MOT recently, the brakes might be a little bit worn or your tyres might be a little bit bald and you don't have as much traction on the road, and so the friction is less and you will travel further without stopping. But on a perfect day with a well-maintained car, your braking distance should actually be much lower than those in the chart that I've just shown you. And there are really good episodes on car magazine shows talking about this, how the advent of ABS brakes and brand new technologies slow down your car much quicker and in much safer fashion than they ever used to. And they argue that actually we should be having higher top speeds. But there are other issues involved. And one of those is the thinking distance. Now, the thinking distance is really, let's think about thinking time. Thinking time is the time it takes if I'm driving, pootling along, la 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 la, and then all of a sudden something jumps out in front of me. My brain has to see the thing with my eyes. That message comes back, so the light goes, bounces off the thing to my eyes. Then a signal goes into my brain. My brain goes, no! And then a signal goes from my brain to my foot. My foot then lifts and goes to the brake pedal, stomping on it and slowing my car to a stop. Now, all of those things are very rapid, but they do take a certain amount of time. And so this means that actually in the time I see the object and between that time and the time I put my foot on the brake, I'm traveling at the same speed as I was when there was no hazard. So I'm traveling further. There is a short period of time before I go, nah, and put my foot on the brake. But during that time, I'm still traveling at the speed I was traveling. So if I'm traveling at 70 miles an hour and something leaps out in front of me like a deer running across a motorway or something, then I have to make that very, very quick decision to slam on my brakes. Also involved in that is checking that a 2-ton truck is not going to destroy me if I slam on my brakes from behind. And so that quick decision has to be made in a very short amount of time. But at that point, I'm still traveling at 70 miles an hour. So until I put my foot on the brake, I'm still going. So the thinking distance is the distance my car is going while I'm thinking. So the time it takes for me to react is going to be affecting the distance that I travel before I hit the brake. Okay, so I've mentioned some of these factors already, but what would be good if you could draw a spider diagram or a mind map of the different ways which we can affect stopping distance, either by increasing or decreasing braking distance or thinking distance, or even both. So our spider diagram will look something like this. We have a thought cloud in the middle, factors that affect stopping distance. And what I'd like you to do, please, is just group them either by colour or by putting them in different sections of your map. But which ones affect thinking distance, which ones affect braking distance, and which ones can affect both. So pause the video, draw your mind map, and then come back. All right, welcome back. So some things that can affect the stopping distance are drugs. If you take drugs, these are going to impair your mental capacity. Stimulants like caffeine make your reaction times quicker. Depressants like alcohol or cannabis make your reaction times much slower. The mass of the car affects the stopping distance, and also the speed that we're traveling, whether or not our brakes are worn, and whether the weather, whether the road is slippery or not, how tired we are. So these three things, drugs and tiredness, alcohol, stimulants. I said 3, that's 2 things. These things affect our thinking distance. If we are stimulated by, like we're on caffeine, then our reaction times speed up, at least temporarily. But if we're taking depressants, such as alcohol or cannabis, or we're tired, then our reaction times slow down considerably. And this can have the effect of causing crashes because we take a lot longer to think and react. And remember, these reactions are happening at the same speed that we start with. By the time we finally put our foot to the brakes, if our reaction times are too slow, then it's already too late. The mass of the car, the slippery road, the worn brakes, all of these things affect the braking distance. Worn brakes and slippery road make the stopping distance even longer, and the mass of the car obviously affects the momentum of the car, as we've discussed before. And the speed that we're traveling affects both, and we've seen that in our chart. Now then, reaction times are an average. Those ones we saw on the chart there, the thinking distance, that's the average person. Some people react faster, some people unfortunately react slower. Another thing that affects this is age. Older people tend to react a little bit slower than young people. Having said that, some young people act impulsively and react too fast to things when they might not need to. So let's have a quick test of your reaction time. We can see what factors affect them as well. So we're going to look at how we can measure that. And there's a very simple experiment, but it needs 2 people to do this. The first thing you're going to do is you and a partner. Now, this could be a brother, sister, cousin, uncle, mother, father, whoever is in your house. As long as they have fingers and thumbs, they can help you. They are going to hold a ruler vertically like this, so that the ruler is just dangling down. You need to place your finger and thumb at the 0 mark on that ruler. Now, without indicating to you, at some point they're going to let go of the ruler, and as soon as they let go, your job is to grasp the ruler. Now, this works with 2 people and not 1. I mean, you can do the same thing with 1 person. You can hold it at one end, put your hand here, let go, and then catch it. But obviously, you know when you're going to let go. If you do it with 2 people and they just let go, then you have to react to the visual cue of that ruler falling. So as soon as your partner lets go, catch the ruler. Don't wait, just catch it. Okay, and the distance it travels is based on your reaction time. So do this 3 times, record it each time you do it, so you can do your own experiment at home. And then I'm going to show you a graph on the next slide. I'm going to include it if you are on my if you're at my college as well, so that you can try and calculate your mean reaction time. So calculate your average reaction time and then compare it to this graph. Okay, so let's say, for example, your partner dropped the ruler and it fell 25 centimeters. Now I'm going to try and draw a straight line here just by using the mouse, so this might go quite wrong. We're going to draw, whoa, my straight line skills are poor, but there we go. We've drawn a line with a ruler, obviously, and this is why you need to use a ruler, folks. 25 centimeters, and we found the point on the line that crosses up here. Now that, despite the fact the line is wiggly, that's not bad. It's actually about here. And then we do the same thing across the other side. Whoa. Okay, cool. To about there. And you can work out your reaction time from here. And from this, I can work out that the reaction time, if it fell about 25 centimeters, is 0.225 seconds, which is pretty good. So wherever your average distance falls, you can find your reaction time using this graph. The further it's fallen, so let's say it falls 50 centimeters, we go up and we find our reaction time is 0.32. Now, obviously, if we were in a classroom, we could compare our reaction time with that of our class, and we could find and do some sort of statistical analysis to see what our average reaction time was. But the average reaction time to this visual stimulus tends to be about 0.25 seconds. Now, what I'd like you to think about and write down is how can we design an investigation to test whether different factors affect reaction time? And remember to do this ethically. Okay, welcome back. So the simple thing that you can do this at home, is you could test your reaction time doing this method at different times of the day. Now remember, don't do this more than 3 times. The trouble with this experiment is you tend to get better and better at it. You get better at the action. Your reaction time isn't increasing. You just tend to get better at the experiment. So it's not a really unflawed experiment. It's not a great one. What you can do is you do it first thing in the morning, you do it in the middle of the afternoon, and then do it later at night. Now, it should depend on how tired you are, and you'll find that your reaction time changes through the day. And some of us, and it will all be different, some of us will be sharper in the morning and have faster reaction times in the morning. Some of us will have faster reaction times in the middle of the day. Very few of us will have sharp reaction times in the evening. And in fact, the later you do it, the longer it should be as you become more tired. Now, some of you will probably find that first thing in the morning is a really difficult time for you, and your reaction times will be really slow because your hormones as teenagers require you to have more sleep and really mess up your internal body clock. So it's a quite interesting experiment to do, so we can try and get other people in your household to do it, see who has the best reaction time at different times of the day. You could also start to ethically look at things that can affect your performance. Now, I am not going to encourage you to take altering substances like caffeine, but this is something we do at A-level biology. What we do is we do this reaction test, and then we give the students a bunch of coffee with their permission, of course, and a control group who don't get coffee, and some who get caffeinated Coca-Cola. And then we test their reaction times using these different beverages. So that is something you could do, but bear in mind, please, you need to get an adult's permission and you need adult supervision. If you are underage, do not try impairing your reaction times with alcohol. But what you could do instead is ask a parent if they'd be willing to participate. I'm pretty sure that I can do different reaction times whether I've had a couple of beers, and who knows, I would imagine your parents might be well up for joining in. It's all in the interest of science. Okay, so here is a 6-mark question then. A group of friends are driving home from a concert late at night. It's raining very heavily, and they're listening to loud music on the radio. Describe the factors that could affect the car's stopping distance and the safety of the journey. Explain the effect each factor could have. Have a go at this, pause the video, and then we'll have a quick discussion. All right, welcome back. So our group of friends are driving home from a concert, hence the loud music, late at night. Now there are 2 factors here. It's late, so the driver could be tired. There are lots of distractions going on. They've just come from a concert. They're probably full of adrenaline, but it's late at night and there are a group of friends. So there's more than one person in the car. So there's a bunch of distractions here. It also says they're listening to loud music on the radio, which can be quite distracting. I found that actually if I've got something on the radio for me, then it helps just soothe my brain, because that's the way my brain works. But if it's too loud, or if I'm too intensely engrossed in the music, that isn't good. So those are the factors which could be distracting the driver. So we have to list these factors and then talk about what's going on. Why are they distracting him or her? and what effect that's going to have. And of course, this effect is going to increase the thinking time of the stopping distance. And remember that this is the time which we are traveling at the maximum speed. So if we are traveling at 30 miles an hour and we have a longer thinking time, during that longer thinking time, we're still traveling at 30. As soon as you touch the brake, you're slowing down. But in thinking time, you're traveling at the same speed. It's raining heavily, so this is going to affect the surface of the road. The road is going to be slippery. This is going to increase the braking distance. So our total stopping distance is going to be affected by the thinking distance, which is affected by a group of friends, it being late at night, so it's dark, the driver has to concentrate, but is being distracted, and then the braking distance is being affected by the weather. Also, you have to take into account some sort of visibility. When it's raining hard, late at night, it's going to be pretty dark, and it depends on how hard it's raining, visibility does actually drop, which increases reaction times even further. All right, simple pyramid plenary, please. Right at the top, write out a question that you have about the lesson. Anything that you've been reminded of goes in the middle, and at the bottom, anything that you have learned today. All right, that's it for today. Stay safe. I'll see you soon.